compounds from their elements, right? And so then, if you look in the back in the appendix, there's a standard heat of formation for water.
So it's just 2 times.
And so it's 2 times that, because then these are 0. Okay? That's why it's kind of a nice example. So, because we had a negative here, then that's why we have this negative here, and we have this is the actual value, and then this is the conversion, and then this is the temperature. Okay? Alrighty? Now, the whole basis of this, because you'll know it goes surroundings, surroundings, whoops, system. But remember, any heat that's given off by the system can only be absorbed in the surroundings, right? If the system absorbs meaning positive, where did it have to come from? The surroundings had to give it, right? Okay, so same amount, opposite sign. Okay? Same amount, opposite sign. Alrighty. So overall, these are the numbers we came up with. The change in entropy for the universe would be considered to be 1,590 joules per Kelvin. Okay? And so we would say that it's a spontaneous process. Or thermodynamically favored or product favored. A lot of these tend to be synonyms. All right. So now, let me go back to here. We have the entropy of the universe. No, this is surroundings, excuse me. Surroundings minus delta S of the system, right? And we want this to be positive. The delta S, wait a minute, let me make sure I've got my, yes, it's plus. I want a plus sign here. Okay, now I gotta remember which way I'm going. This way is the way I'm going. Alrighty, so that's my equation I started with. Before I get to this next slide, I want to say we have the delta S of the universe. We have, this is going to be the delta S of our system, right? And here we said, okay, we're going to call this the delta H over T, right? Right? And so now we're going to multiply through by negative 1 over T. And we should get that the negative T times the S of the universe is equal to our delta H minus T delta S of the system, and we agreed that these were both system values, right? Okay, now we're going to go back and we're going to say that this negative T delta S for the universe, that change, whether it's positive or negative, is going to be represented by delta G is equal to delta H minus T delta S. And we drop the system, okay, because we want to, we'll just assume from now on that all our delta H's and all our delta S's are for the system, okay? So all of this was just an attempt to make this not be something that I just pulled out of my hat, okay? Nobody's gonna ask you to do the actual entropy change for the universe. Possibly your homework will involve a couple of questions just so you realize that the entropy change in the universe is what has to be positive or increasing, okay? Alrighty, so now what we're gonna do is we're gonna look at general criteria for spontaneity. When we do questions like this, we do them both with numbers and we do them with general. So if we predict whether a process will be spontaneous, and remember for delta G, what do we need to have in order for it to be spontaneous? A negative value equals spontaneous. Okay? If you have trouble remembering that, remember that we have a delta H here, and remember we've said that exothermic doesn't always mean that it will be spontaneous or thermodynamically favored, but it will certainly greatly contribute to that process. All right, so if we have an exothermic process, so type 1, what's our type 1? And hopefully you can see that we can have 4 different options. We can have them where they're both less than 0, we can have them where they're both greater than 0, and we can have them where they're each one of each. So our first type is where we have our delta H for our system is less than 0. That would be exothermic. And we have, that should say, okay. And so here, if we have our, if we have less order, gosh, I looked at that and I was like, but that's more randomness. Okay, so less order means more disorder, right? So I don't know why that looked funny to me. All right, so our delta S is greater than 0, and so this is spontaneous under all conditions. You wouldn't even have to do a calculation. If you have an exothermic reaction where you can, by looking at reactants and products, looking at a phase change or whatever, see that the entropy is increasing, that would be spontaneous under all conditions. Now, let's take a look at this. What does that mean? If we have a negative here and we have a positive here, both of these terms can only what? Contribute to a negative value, okay? So it doesn't matter what the temperature is. This reaction will be spontaneous for all temperatures, okay? Now, what if we also, we're going to stick with our exothermic process, but what if our entropy decreases, okay? Well, then this overall, if we take a negative number and we subtract it, overall this is going to be positive, right? So it's going to depend on the relative magnitudes of delta H and delta S, and it will be